If we had to solve this triangle, we can't use a primary trigonometric ratio or Pythagoras' theorem because we don't have a right triangle. To use the sine law, we need at least one pair of opposites where we know both the angle and the side across from it in order to set up those ratios. We don't know this side, we don't know this angle, we don't know this angle. So there's no pair of opposites that we have, so we also can't use the sine law. But there is another strategy we could use, the cosine law. The cosine law is derived from a combination of Pythagoras' theorem as well as the cosine primary trigonometric ratio. So let's take our oblique triangle here, break it into two right triangles, and then take a look at where this formula comes from. If I take this triangle on the left, that's a right triangle, and I'm looking for angle C, I can use cosine and set up the adjacent side divided by the hypotenuse, but the adjacent side only goes from here to here. Side A, opposite from angle A, is this entire length here. So what I'm going to do is break this triangle base into two separate bases. So I'm going to call from here to here just side X, and then the second one side Y, knowing that A is that entire length of the triangle. So then we can go over here and say, okay, so the cosine of C is going to be the adjacent side divided by the hypotenuse, and then I'm going to rearrange this. So in order to get that B off of the denominator, I'm going to multiply both sides by B. B divided by 1 over B will leave us with 1x on the right. And then I'm also going to set up this triangle in terms of the Pythagorean theorem. So we know that B is the hypotenuse, so B squared is equal to x squared plus h squared. And I'm going to relabel this side here. So instead of y, if I know that my entire base from here to here is side A, and this is side x, if I take side A, subtract side x, that will give us a side length here of A minus x. We can then set up the second triangle here on the right using Pythagorean theorem. So now C is my hypotenuse, so C squared is equal to h squared plus this A minus x squared. And then if we go to simplify this, I'm going to remove this brackets by squaring that binomial. And we know when we square a binomial, we're going to square the first term, double the product, so we have a negative ax times 2 will give us negative 2ax, and then we're going to square that last term. So a negative times a negative becomes a positive. And then you can see that in our ultimate formula here, we only have a, b, and c for variables. We don't actually have an h here. So let's go ahead and rearrange this. We can see that h squared plus x squared equals b squared. So I have an h squared, I also have an x squared, so I'm going to rearrange those so that those are together. And then we can take this h plus x squared right here, and if this is equal to b, let's go ahead and substitute in a b for that piece. Now we're getting closer, but you can also see that we need to substitute this x for something. And if we go over here, we can see that x equals b times the cosine of c. So let's go ahead and substitute this in the place of x. And now we have the cosine formula. It's not identical to this one, but what you should notice here is that there's only one angle in the formula. That's my capital A here. The angle that we have in that formula is going to be opposite from the side that we're solving for. So here I've got angle C in the formula, which is opposite from side C that we're solving for. It doesn't matter the order in which you add the other two sides, just like it doesn't matter the order in which you multiply the other two sides. So any oblique triangle that you have, if you know two sides with the angle in between, so you're looking for that pocket. So if this is the angle that we know, and we know the two sides that contain that angle, this is a case where we could use the cosine law. Or if we don't know any angles, but we do have all three side measures, we can also take this formula, rearrange it, and solve for missing angles. Let's take a look quickly at how we would go about that. So for solving for an angle, so this is the angle we have in this formula, I'm going to keep this cosine of C, try to isolate that by removing all of these other pieces. So we're going to do order of operations in reverse. So we're going to begin by moving any pieces that we're adding or subtracting, and then we're going to remove any pieces that we're multiplying or dividing. So if I'm trying to isolate the cosine of C, I'm going to divide out that negative 2ab, and I'm going to do that from both sides. So on the right, negative 2ab divided by negative 2ab will isolate that cosine of C, and then on the left, we end up with this. Now, we don't like to leave a negative in the denominator, so we're going to move it up to the numerator, and when I do that, I'm going to distribute this in, and all of those signs are going to end up flipping. And then because we also don't like to leave a negative sticking out front, I'm going to take this first first term and just kind of tuck it behind there and rearrange the order so that we end up with something that looks very beautiful. So again, what you want to notice is that the angle that we are looking for is the side that we're subtracting in the numerator. It doesn't matter the order in which we add the other two sides, nor does it matter the order in which we multiply those other two sides. So if we're looking for this angle, the only time side C appears in the formula is right here. That's the piece that we're subtracting. And then when you go to enter this into your calculator, remember we need to calculate the entire value of the numerator, the entire value of the denominator, and then divide those two values. So you can type this whole thing in, press enter, and then when you go to put the denominator in, just remember you have to put that in brackets to tell your calculator that we are dividing by the whole product down here. This first example, we're asked to solve triangle PQR. So the first thing we want to do is set up a diagram. I'm given one angle, and I want to draw that angle as my base angle here, just like we did with the sine law. Because it's obtuse, we're going to try to draw it as close as we can. It's not going to be drawn to scale, but we can at least get it somewhat proportionate. So if this is angle P, side P has to be across from it. And then just the way I've drawn this appears to be my shortest side. So I'm going to put that opposite from angle Q, which makes this side Q. And then side R has to be opposite from angle R. I can't use a primary trigonometric ratio or the Pythagorean theorem because I don't have a right triangle. I also can't use the sine law because you can see we don't have any pair of opposites here. We do, however, have that pocket. So we can see how this little angle we know. We also know the two sides that contain that angle. So I'm going to go ahead and set this up, and we're going to then solve for side P first. So if I'm solving for side P, then angle P is the angle that we're going to put in here. It's also the only one we happen to know. So I'm going to have P squared equals one side squared plus the other side squared minus 2 times the first side times the second side times the cosine of that angle. Now, when we go to enter this into the calculator, the first thing you want to do is go into mode, make sure that you are in degree mode, and then we're just going to go second function quit to get out of there. And then we're going to type this piece on the right-hand side exactly the way we see it. So we're going to go 37 squared, and then plus 51 squared, and then minus 2 times 37 times 51 times the cosine of that 126 degree angle, and that is going to give us P squared. Now we want P, so in order to get P, we're going to square root that. So we're going to go second function square root, and then second function, press that negative key, and it's going to put the answer in there, and then hit enter. And so now we know angle P has a value of about 78.6, etc. degrees. We now have two remaining angles that we have to solve for. You can use the cosine law again to solve for angle R, and then the cosine law again to solve for angle Q. That will give you the correct answers in all of those cases. If, however, you decide to now use the sine law, because we do have a pair of opposites and the sine law is a little less cumbersome to use, you now want to start with the smallest angle, which we know is going to be opposite the smallest side. So this is my smallest side. I'm looking for this angle Q that's opposite from it. And the reason you want to do that is because this angle that's originally given to you may not be obtuse, in which case there could still be an obtuse angle in the triangle, but you know there can only be one. For example, in this triangle we have a pocket. So we have a side, the angle in between is known, and this other side. We can use the cosine law to begin solving for side N. We now have a pair of opposites. We could use the sine law to solve for either angle M or angle L. This is not an obtuse angle. So one could still exist in the triangle, but because there can only be one, if I start with the smallest angle, I know that angle won't be obtuse. So in this particular case, this is my smallest side. I'm going to begin by solving for angle L. Once I know two of the angles in that triangle, I can subtract from 180 to get my last one. Example here. Once I've used the cosine law to get this side, I've got two angles left. I can see that this is my smallest side, so I'm going to begin by solving for angle Q. So we can go ahead and set up our pair of opposites. And then remember, if you're going to start with an angle on top, we continue with an angle on top. So we can go ahead and cross multiply and then solve for that angle, which is now 22.36 degrees. And once we now know two angles, we've got that 120 126 and we've got that 22, we can subtract those two from 180 degrees and that will give us our third angle. And then we can go ahead and check. So we do have the longest side opposite the largest angle. We have the smallest side opposite from that smallest angle Q. The other thing you can do is that we know in the sine law, the sine of the angle divided by the side opposite from it is equal to the ratio of the sine of another angle divided by the side opposite from it, which is equal to the sine of the third angle divided by the side opposite to that. So we could always say, okay, so let's take the sine of this angle and divide by the length of p. Now, when you put this in your calculator, a bracket will pop up when you press sine. Remember, you have to close it after 126 and then divide, and we're going to get a ratio of about 0.01, etc. And then we're going to take the sine of our next angle, angle Q, and angle Q is opposite from that 37. So when we divide those two, again, remember to close your bracket, we get that 0.01, etc. And then when we take the sine of our last angle, angle R, that is opposite from side R, which is that 51 meters. And you can see that, in fact, those three ratios are equivalent. Therefore, we have a triangle that works. In our next example here, we're given the measurements of the three sides in the triangle. So I'm going to go ahead and draw a triangle, and then I just labeled them based on how I drew this. So my longest side is the base, so I put the longest measure there, which means opposite from that would be angle Z, and then my shortest side would be this one here, so then opposite from that has to be angle Y. And then we're going to begin with the largest angle first, and you'll see why in a second. So I'm going to go ahead and set it up, solving for angle Z. I know that's the largest angle because it's opposite from the longest side. That side that it's opposite from is the side that I'm subtracting. And then when we put this in the calculator, just remember you have to put that denominator in brackets. Type this in, we're going to begin with the numerator. So we're going to have 2.5 squared plus 4 squared minus 5.7 squared, and then I'm going to press equals to calculate that whole value, or you can put it in brackets if you want. And then we're going to divide by, now we do have to put this in brackets, so we're going to go bracket 2 and then times 2.5 and then times 4, and then we can close the bracket. And so that's going to give us the cosine ratio. It gives us a negative ratio. So if you go back to the cast rule, we know that cosine is negative in quadrants 2 and 3. That tells us that we are going to have an obtuse angle. We're obviously not going to be down here because our triangle cannot have greater than 180 degrees for an angle. If you get a negative ratio, that tells you the terminal arm will lie in quadrant 2, so we are going to have an obtuse angle. So now in your calculator, you might be able just to take the inverse cosine of this with the negative and get the right value. But if your calculator gets all finicky with that, go second function cosine and then just leave the negative off and enter that 0.512. So let's try this here. So we're going to go second function cosine, and I'm just going to leave off the negative and go 0.512. And then we can see that that's going to give us the reference angle. And then if we think about our angles in standard position, we know that if the reference angle is 59 degrees, that's going to give us a 59 degree angle here. 180 minus 59 will give us 121 degrees, which is going to be the measure of that angle Z in our triangle. Now your calculator, like mine, if we enter the numerator divided by the denominator and get that negative 0.512, I can just go second function cosine, second function answer, and my calculator will give me that angle there. But we want to be aware of what's happening, because you can now see why, if we don't have any angles in the triangle, when using the cosine law, we always want to begin with the largest angle first. We can only have one obtuse angle in a triangle. So we've now solved for that angle. We've got the value of that. I know my other two angles happen to be acute. If we solve for those two angles using the cosine law each time, it's not really a problem. We're going to get the correct values in all three cases, but you can see that the cosine law is a little bit more cumbersome than the sine law. So if we now switch to the sine law, because we do have a pair of opposites now, we can solve for either angle X or angle Y. And with the sine law, we could potentially have the ambiguous case where there's more than one solution and we have to determine, is it acute or is it obtuse? So using the cosine law, if you start with that largest angle, we've already identified there is an obtuse angle angle, this is it. We know that those other two angles will be acute. Their terminal arm will lie in quadrant 1. Because we've already identified that obtuse angle in this triangle, it doesn't really matter which of the other two we do first, but my smallest angle is going to be y. So I can set up the sine law and solve for y, and then I can subtract the two angles that I now know from 180 degrees to get my last one, and then just check to make sure that everything works out. And in our final example, we're asked to solve triangle ABC given the coordinate points for A, B, and C. So the first thing we want to do is go ahead and plot those, and then we need to know what the lengths of those three sides are. And as you can see, they're not going to be exact measures here. So what I'm going to do is actually draw in a triangle, and then I can use Pythagoras' theorem because we have a scale going up by 1. Each of these squares is going to be 1 unit, and then we can go ahead and calculate each of those lengths. So to begin with, if we're looking for the length of line segment AB, this is the hypotenuse. We know this is a right angle here. So we can see that we're going 6 squared plus 5 squared, which is 36 plus 25, the square root of 61. There is no perfect square in 61, so I've got the exact length of that line segment. We can go ahead and do the same thing with those other two line segments, and then there's no perfect square in here, so I'm going to just leave that as the square root of 122. Because AB is the same length as AC, that tells me that we have an isosceles triangle, so I know those two angles are going to be the same measure as well. We now have the measures of the lengths of all three sides. In order to get the angles, I can see that this is the longest side, so I'm going to begin with that largest angle opposite from it, which is angle A. So we're going to add up the two sides. If I'm solving for angle A, I'm subtracting that side A, which is in this case just that side BC. And then we know that when we go to square, it's going to cancel out a square root. In the denominator, if I have the square root of 61 times the square root of 61, 61 times 61 is going to give me a perfect square. When I square root it, I will just have a value of 61. And then we're going to multiply that by 2. 61 plus 61 is 122. Minus 122 gives me a numerator of 0. I know that this angle here is going to be 90 degrees because if we take second function cosine of 0, we'll get 90 degrees. That's a quadrantal angle. So remember back, if we have a 90-degree angle, we know the cosine ratio adjacent over hypotenuse. That's the x over the radius. If my x-coordinate is 0, I'm going to be right on that y-axis there. So that also tells me if angle A is a 90-degree angle, this is a right triangle. Angle B has to equal angle C because it's an isosceles triangle. So take this other 90 degrees that adds up to 180 here, split it evenly amongst those two angles, and I know B is 45 degrees and C is 45 degrees. 180 degrees in the triangle. Remove the 90 we know, split the other 90 evenly. We know those two angles are equal, and we now have all three angle measures, and we have all three side lengths.